Welcome everyone to NSTA Web Seminars, where you can find live interactive learning at your desktop. Today's presentation is part of our series on the NGSS core ideas, and today's focus is on Earth's place in the universe. Our presenter is Julia Plummer, and we do have Ted Willard online with us to provide information about the NGSS. My name is Bryn Slate. I will be moderating. Jeff Lehman is here at NSTA headquarters to provide technical support. And before we jump into the presentation, I did want to remind everyone to visit the NSTA Learning Center, which is your online portal for teacher professional learning and the home of over 11,100 resources. As many of you know, we've got almost 4,000 resources for free, and that number is always rising, so continue to check out what we have new there in the Learning Center. Resources can be added to your My Library space, so you can get to those anytime you've got your internet connection. Community forums are a great place to connect with other science teachers, discuss content, pedagogy, and the NGSS, amongst other things. We do have online advisors who are available via our live support button. If you need some help finding particular resources, they know the Learning Center very well and are always eager to help you find the things that you need. We also have free tools, such as our PD Plan and Portfolio tool that can help you organize what you're doing for your professional learning and to meet your goals. Everything is available by going to learningcenter.nsta.org. At this point, I'm going to introduce our presenters. We've got Ted Willard, Director of NGSS at NSTA, and he's going to be facilitating our Q&A after providing just a quick introduction to the development of the standards. And then we have Julia Plummer joining us from Penn State University. So at this point, I will turn it over to Ted to get things started. Welcome, Ted.
Thanks, Bryn. Welcome, everyone. Happy to get going here. We've, in the last 4 sessions, our series have covered the physical sciences. Tonight we start up with the earth sciences, or I should say earth and space sciences, particularly tonight as we deal with Earth's place in the universe. The standards, NGSS, the Next Generation Science Standards, were developed by 4 organizations: the National Academies of Sciences, Achieve, the National Science Teachers Association, my favorite, and the American Association for the Advancement of Science. And as many of you know, the standards went through sort of a 2-stage process. There was first the development of the framework for K-12 science education, which then was used as a guide to develop the standards, and these standards which are going to be used to guide assessment, curriculum, instruction, and teacher professional development. Let's start talking about the framework itself. It was developed and released in July 2011 by the National Academies of Sciences. And the big key here was 3 dimensions: the scientific and engineering practices, the cross-cutting concepts, and the disciplinary core ideas. I hope all of you have had a chance to look at and read the framework. If you haven't, you really should. You can get a free PDF from the National Academies Press, or you can also buy a hard copy from the NSTA Science Store. So here's an example of the scientific and engineering practices, and we have an archived set of web seminars about these. Things like asking questions, developing models, using mathematics, engaging in argument from evidence. These are the things that we want our students to be doing as they try to develop an understanding of disciplinary core ideas and cross-cutting concepts. And speaking of cross-cutting concepts, here's a list of the 7 that are there: pattern, scale, systems, structure, and function. These are things that are not unique to life science or earth science or physical science, but cut across all of these different disciplines within the sciences. And that then brings us to the disciplinary core ideas themselves. What you're probably most familiar with, we have life, physical, earth and space, and engineering. And each of these subject areas breaks down to smaller categories, such as Earth's place in the universe, Earth systems, and Earth and human activity. And that then gets broken down further. So there's examples here of how Earth's place in the universe has further breakdowns. Now, all of that was established in the framework, and then the standards made use of that. And so the standards were developed by a group of 26 states, outlined in blue there, in a process that was managed by Achieve. These are the lead state partners. And even though only these states in blue were involved in developing the standards, all states now have the option of adopting the standards. And so our current, first I got ahead of myself here to note that there are 41 writers from around the country that were involved in the development of the standards. And here's where I was jumping to, is the current state of adoption is that we have now 8 states that have adopted the standards, and the ones in yellow have undergone some sort of process at the state level in terms of looking at it, some sort of formal piece, either the State Board of Education or State Department of Education has been doing some work, and I'm sure more will be coming soon. So here's an example of the standards. We have at this point here, develop molecular models of reactants and products to support the explanation that atoms and therefore mass are conserved in a chemical reaction. And so that performance expectation is a description and guidance really to the developers of assessments of what students should be able to do at the end of instruction. It's not meant to be specifications for what a teacher needs to do in the classroom. And that is an important distinction to make here, is that teachers are expected to get their students to this point, but it's not just by having them do this. There's a lot of work teachers need to do in terms of deciding how they can best help their students gain the understandings and the abilities necessary to do the performance expectation. But the performance expectation does have these 3 elements in it. It has practice, so we have developing molecular models to support an explanation, and that's described down here in the blue box. We have this idea of reactants and products, and that atoms and therefore mass are conserved in a chemical reaction. Each of these pieces is dealt with in the disciplinary core ideas. And then we have the cross-cutting concept that atoms and mass are conserved in a chemical reaction. And that leads to this concept about energy and matter, that matter is conserved because atoms are conserved in physical and chemical processes. And so all of these 3 different elements tie together to give you the performance expectation. And so with that in mind, I'm going to pass things on to Julia so we can dive deep into Earth's place in the universe. Off to you, Julia.
Thank you, Ted, and welcome everyone. I look forward to speaking to everyone during this presentation this afternoon or evening, depending on where you are in the world. And, okay, I'm just still getting used to the system. All right, so let me go on to the next slide and tell you a little bit about myself. I'm an associate professor of science education at Penn State University, and my background is in astronomy. I did a combined PhD in astronomy and education at the University of Michigan. And this built on my background and my interest in teaching and learning because I spent 12 years teaching in the planetarium and other informal environments focusing on astronomy. I also spent a number of years teaching astronomy at the college level. And so that's led to where I am now at Penn State University, where I actually teach classes for pre-service teachers learning how to teach science. And my research focuses on how we can learn ways to support students and teachers in astronomy across preschool through 12th grade in both formal classroom environments and informal environments as well. So I thought we'd find out maybe a little bit more about who's in the audience. And so Bryn, maybe you could help us do this interactive poll.
Sure thing, Julia. Everybody will be using our screen marking toolbar. Go ahead and pick the virtual pencil, which is the 3rd button down. And then feel free to put your mark up in the appropriate row. I'll point out to folks, the pencil is the best choice for getting your mark to stay up there. If you do use the pointer with the smiley face or the check, just click one time, then it'll stay up. If you do move around a little bit with that pointer, it'll jump with you. But if you want your mark to stay up, do your check mark with the pencil. And we'll give everybody just another moment or so to do this. But definitely, Julia, it looks like we've got a lot of teachers, classroom teachers joining us, but very cool to see those pre-service teachers and supervisors, our college, university, and others joining us as well.
Yeah, this is great. It is nice to see the diversity. I'm also enjoying some of the artwork that I'm seeing as people make their selections. Great. So hopefully most people have been able to indicate that we've got a lot of practicing teachers. Shall we go on to the next slide, Bryn?
Sure, sounds great.
Okay, so now in the next one, let's find out what your focus in grade or age level. And so if you're looking across, you can mark on multiple places, preschool, 3rd grade, 6th grade, get a sense of this. Great.
And Julia, I'll just remind those who may be on mobile devices, either tablets or smartphones, your screen marking toolbar isn't accessible when you're on those devices. So just type into the chat window for any of these markup questions. And I do see a number of folks are doing that, so great job. Thanks for catching on. In terms of the grade level split, Julia, it looks like we've got across the board, but maybe middle school? It's hard to tell.
Yeah, it does look strong at sort of the upper elementary, middle school, but also quite a few people in high school, college, as well as some in the kind of early elementary focus. So this is good. I'm going to try to cover information that spans this range in the presentation today, so hopefully everyone will hear something that's relevant to the work that they do. All right, thank you everyone. I'm going to move on to the next slide then. So the goals of this presentation are to give us an opportunity to think more in depth on how the Next Generation Science Standards addresses astronomy, and to focus on how it addresses this in a notion of developmental progression, so that we're not just covering a number of topics here and there throughout the different grade bands in the standards, but that we're looking at this as a progression of supporting increasingly sophisticated explanations about the Earth's place in the universe. And as I talk about that, I'm also going to talk about how the way we design instruction should, in the way that we assess students' understanding, should look at this as integrating our focus on the content with the scientific practices. And finally, I'm going to talk a bit as we go through the different topics I want to address on how important recognizing spatial thinking and the complexities in this domain and why students have so many challenges, and that can often go back to the difficult spatial thinking required in astronomy. So as Ted started pointing out in his earlier slides, the Earth's place in the universe is just part of the larger coverage of science content in the life sciences, the physical sciences, and the earth and space sciences. And so the Earth's place in the universe can also be broken down into 3 kind of subcategories: the universe and its stars, the Earth and the solar system, and the history of planet Earth. So in this presentation, I'm going to be focusing on primarily the first 2, the universe and its stars, the Earth and the solar system. The third area, the history of planet Earth, includes a lot of what we might traditionally call geology. And so in the interest of providing some depth of examples and some instructional examples, I decided that I couldn't actually do justice to covering all of the content in the Earth's place in the universe. So I'm going to pick a few coherent examples that build from early elementary school through high school, but that means I won't be able to do all of the topics that are covered in this part of the Next Generation Science Standards. So one of the ways that the Next Generation Science Standards draws from the framework, so as Ted and I think Bryn have mentioned, the standards built from an earlier document called the Framework for K-12 Science Education that started to provide a guideline to how to develop these standards. And within it, it talks about the idea of disciplinary core ideas. And so these disciplinary core ideas are those that serve as key organizing concepts within the discipline. And they have explanatory power, so that these disciplinary core ideas are those that can be used to explain a wide variety of phenomena. They're also generative. They're a key tool for understanding or investigating more complex ideas and for solving problems. And finally, disciplinary core ideas are those that are teachable and learnable over multiple grades in increasing levels of depth and sophistication. So as we look at the concepts in astronomy under Earth's place in the universe, I sort of drew out three things that I think are clear disciplinary core ideas. They have this broad power to explain a lot of phenomena that we traditionally associate with astronomy. Many astronomical phenomena observed from the Earth can be explained by the relative motion of the Earth and other objects as they move in the solar system. Another disciplinary core idea is the idea that the motions and properties of objects in our current solar system, so the way the solar system is now, those can be explained by how the solar system was formed from a cloud of gas and dust about 4.5 billion years ago. But we can also explain the current structure of the universe using the Big Bang Theory as another disciplinary core idea. Another way that the Next Generation Science Standards tries to communicate the importance of these disciplinary core ideas is by this idea of looking at progressions of understanding, progressions of the way students learn to explain in increasing sophistication the Earth's place in the universe from these different grade bands. So starting at the K2 level, we see that the way that the standards are written, they emphasize a focus on what can be observed from an Earth-based perspective, the patterns of movement of the sun, moon, and stars. And then you can build on that at grades 3 to 5 in using the Earth's orbit or rotation and the orbit of the moon to start explaining these observational patterns. And then this continues to build in middle school as students develop even more sophisticated explanations for the observations they can make from an Earth-based perspective, such as eclipses, lunar phases, and seasons. And then at the high school level, this moves into an increasingly complicated and sophisticated understanding of how the Earth's tilt and orbit can lead to climate changes such as ice ages over extremely large timescales compared to those earlier timescales studied at the elementary grade levels. But we can also look at progressions that move from this elementary level into middle school that move to understanding the properties and motions of objects in the solar system and how they're held together by gravity, and that those can become observations that are evidence for the explanation of how the solar system formed, or we can develop increasingly sophisticated models for explaining how objects move, such as Kepler's laws of motion. Finally, if you look along the bottom, you can also see a progression of understanding of our observations of stars, how our location is part of the Milky Way galaxy, which is part of many billions of galaxies, and then even moving on to understanding more detail about stars as well as evidence for the Big Bang. And in this presentation, as I said, I'm going to focus in more depth on a few areas of astronomy. And so I've highlighted the areas that I'm going to provide examples of how students can engage in this, how this is reflected in the NGSS, and how we engage students in scientific practices. All right. Now, as Ted mentioned earlier, one of the things that the NGS is trying to do is move away from a focus that's either purely on content alone or purely on, say, inquiry alone, and look at a fusion of these ideas in how we design instruction and how we assess students. So that in designing the standards, we're designing performance expectations, what we hope students will be able to perform after the instruction they engage in our classrooms. And that crosses the core disciplinary ideas, so the one we're focusing on today, the Earth's place in the universe, with the 8 scientific practices, asking questions, modeling, planning and carrying out investigations, etc., as well as the cross-cutting concepts that we see move across the different disciplinary core ideas, so all the domains that see the importance of patterns or energy or systems thinking. And so in this next slide, and I'm going to have Bryn help us with doing some interaction here in just a minute, but what I want you to think about here is one of the ways that the NGSS talks about the Earth's place in the universe in the framework is it draws out kind of this smaller concept, the idea that the patterns of motion of the sun, moon, and stars in the sky can be observed, described, and predicted. And so as you think about that concept and you think about the scientific practices, I want you to think about which of these scientific practices do you think would be easiest or most natural to fuse with this concept that I've put at the top here. And so think about if you were going to develop some form of performance expectation, what you would hope students would be able to do with this idea, which scientific practice would you choose to integrate it with, either in your instruction or in designing assessment? So, Bryn, I think what we'll have people do is maybe use their checkmark tool, and you can choose as many as you like.
Sounds great, Julia, and it looks like most folks are already jumping on this one. If you joined us a little bit after our intro, the screen marking toolbars are, the toolbar is right alongside of your participant window, and your pencil, virtual pencil, or your highlighter is the 3rd button down. So feel free to grab that and put your markup on the ones that you think you might be using.
Great. And I think people are starting to see this idea that there's not one way to do this, that any of the concepts drawn from the disciplinary core ideas could be taught in ways that integrate any of the scientific practices, and we could potentially develop performance expectations or assessments that build in this fusion of that concept at the top with the scientific practice. And so I see pretty much we've used up all the space available, so why don't we go ahead and move on, and I'm going to show you what the NGSS actually selected to fuse with that idea as an example of what could be potentially assessed from the next generation science standards. Let's see if I can make that work. There we go. So what we see here is an example from the NGSS of a performance expectation. And I'm going to look at the first one, ESS 1-1, use observations of the sun, moon, and stars to describe patterns that can be predicted. So if you look below that, you see disciplinary core ideas. And so it's drawing upon this disciplinary core idea, patterns of motion of sun, moon, and stars can be observed, described, and predicted. You can also see that it's using the cross-cutting concept of patterns. That one's pretty obvious. And to develop this particular performance expectation, the NGSS writers selected analyzing and interpreting data. So the way it's written, use observations, suggests that a potential way that you could be assessing students' understanding of this disciplinary core idea, this is actually at the first grade level, is to see how they're able to use data, observations of the sun, moon, and stars to describe patterns that can be predicted. But based on your answers before, I'm thinking that many of you can see many other possible ways to teach this idea integrated with the practices or to even assess this idea. Now there's one other thing I wanted to call your attention to, because some of my astronomy colleagues wanted me to point this out, and let me just circle this. So the next generation science standards, they decided to use the term space systems as opposed to using the term astronomy that astronomers are more used to. But this now aligns it with how a lot of the standards are being talked about in language that really focuses our attention on the idea of systems and system thinking. So rather than talking about astronomy, it's being referred to as space systems. All right. So I think we're actually at the point where Ted's going to guide a discussion of any questions so far.
Great. And so, folks, if you want to put your questions up on the in the chat window, we will take those and pass them on to Julia. Julia, I don't know if you want to tackle this one. I'm also happy to help if you'd like to. Carrie is asking, does NGSS want us to use their practices, or is it just a suggestion?
Okay, that's an interesting question. I would have to guess that they're saying that they want you to use their practices, but I think one way to look at it is to really look at how are the science practices described in the framework. The framework goes into more detail than is really, you can see just from the writing there. Mm-hmm. And so in general, I think the practices that are described in the framework cover a lot of what we really consider to be the practices of science. Some of us may use different language, and I don't know that they really prescribe the exact language you would use. But another way to look at that is, if you look at just the performance expectation, what it's not saying is that if you're teaching astronomy, you should really only focus on analyzing data when talking about the patterns of the sun and the stars. That's not what it's saying. It's saying you really should think about any way you want to integrate the science practices in astronomy.
Yeah, I think that's a good point there. This distinction between assessment and instruction. That I'm wondering if what Carrie's referring to here are what this performance expectations specifically call for, which are really only meant to be a mandate to assessment developers, not to classroom teachers. Classroom teachers can go and blend practices and core ideas and cross-cutting concepts any way that they want to, which was one of our earlier points here. So Luana is having, I'm sorry, my window didn't scroll down as well. Stacy asks here, what's the most important, and it just scrolled on me, what's the most important, could they renamed astronomy to space systems because astronomy is more theoretical? That's a question Jeremy asked.
I'm not entirely sure. I was not involved in any of the conversations in which space systems were selected. I could understand using astronomy instead of astrophysics, but yeah, I'm not entirely sure if that's part of the rationale.
I liked your point about the idea that they were very into systems in other areas and put it together. So,
I'd like to address Rachel's question. Mm-hmm. Rachel asks, in trying to unpack performance expectations, teachers were trying to determine if moon phases fits in 3 to 5 or 6 to 8. And I'm wondering if this is about trying to figure out where does phases of the moon actually fit in the framework and in the standards. I felt that it was a little bit unclear at times as to whether phases of the moon were at the elementary or the middle school level. It's most explicit at the middle school level if you look at how it's written.
Great. Paula, I'm sorry, we're not going to, at this point in time, try to go through what the difference between each individual state standards here. But we will talk about Rose's question here. For first graders developing their observations about daylight, etc., what safety precautions are emphasized to prevent their looking at the sun?
Okay. Well, of course, the NGSS doesn't go into that kind of detail in terms of instructional design. I think from my own experience, obviously we do want to emphasize safety and encourage children to obviously not stare at the sun. But we are going to talk a little bit about this a little bit later with some examples, but I think focusing children on how their shadows can provide evidence for where the sun is and tracking that is a way to get them to focus on not looking exactly at the sun, but to look at evidence for where the sun is.
Great. I think we're good here for the time being. People can continue to post their comments or their questions, and we can follow up with some more into our next question break. So, but for now, Julia, if you want to move on, we can do that.
Great. Okay, so in this next part, let me give you just a little introduction to where we're going to be going, and then I'm going to have us do another poll, or actually the first poll using the poll option. I'm going to start by looking at the kind of kindergarten through second grade band, and then we're going to move into the elementary and middle school, and then into the high school. And obviously, one of the most obvious concepts that we address in instruction in astronomy is the day-night cycle. So just as an introduction to starting to think about what you think is most important to emphasize in teaching about this concept, I want you to think about what's important for children to understand. How the sun appears to move across the sky, how the Earth rotates every 24 hours, both the apparent motion of the sun and the actual motion of the Earth, or D, this is not actually an important concept for children to learn. So we'll use the poll button that some people are already using.
Great job, everybody, and I'll just remind folks where that's located. If you joined us after the intro, it is right under your own name at the top of the participant window. You'll see the little square button with an A on it, and you can mouse over that to select your best answer. And it looks like we've got about half of folks have submitted an answer. Thank you for doing that so quickly and giving us your interactivity on this one. It's always good to get that immediate feedback and see what people are thinking in real time. We'll go ahead and give about 5 more seconds before we lock the poll, and then in just another moment here we'll be able to see kind of the breakdown of what everybody is thinking. So I'll go ahead and lock the poll now and put up our graph, and then I will move this a little bit over so we can continue to see all of our text, and I'll turn it back over to you, Julia.
Great, thank you. So looks like we have a strong tendency to select answer C, and this reflects my own belief about what students should learn, and it does reflect how the NGSS builds from understanding phenomenon from where children can make observations. So that would be answer A, how the sun appears to move. But then developing explanations using models, understanding, in this case, what the Earth is actually doing in the Earth's rotation. So that's sort of giving a hint of where we're going to be going on the next slides. And I was happy that no one selected D, that they don't need to understand that, so that's a good step. So as I said, I want to start with kind of the kindergarten through second grade band. And as we talked about, the performance expectation reflects this idea of using observations of the sun, moon, and stars to describe patterns that can be predicted. So this is all from an Earth-based perspective. And this implies that we need to prepare students to understand how to do this kind of work by giving them opportunities to do things like gathering their own observational evidence. Could be one thing to do. Opportunities to analyze observations in order to make patterns, and opportunities for them to learn how to develop representations, which is an aspect of models and model use, so they can use that for predictions of future observations. And so in the next box, an opportunity for us to interact a bit, I want you to think about how could children in kindergarten through second grade participate in experiences that would allow them to make observations that would help them have evidence to determine the daily pattern of motion of the sun, moon, and stars.
And so for this,
this one, yeah, go ahead,
I was just going to say that for this one, we will take answers in the chat, but for those of you who are interested in typing up on the screen using that text box tool that we tried out in the intro, go ahead and just raise your hand. Click on that raised hand button, which is the little hand right under your own name, and I'll give you the tools. We'll take the first 4. Great. Okay, so Kirsten, I'll go ahead and give you the tools. Jeremy, Elaine, and then Paula. And for those of you who came in later than number 4, we'll get you on the next round, okay? And feel free to type response in the chat. So this will be good. We'll take a few moments here to see what comes into the chat window. We'll also take a closer look at what our 4 volunteers, Kirsten, Jeremy, Elaine, and Paula, have been so kind to share with us by typing up onto our whiteboard.
This is great, and especially since we can have a lot of ideas flowing through our chat window, as well as people adding their, our 4 participants adding into the chat box on the screen. I've seen a lot of ways to engage students in making observations outside, shadow tracking. I saw sundials. I've had fun with sundials with college students. Doing a moon phase daily chart. A lot of you are focusing on ways that students should actually be collecting data. So that's important too. How are they recording their observations? Good, I think I saw a portable planetarium and some using Google Space. So we're also looking at some secondhand ways of making observations. So both direct observations that children can make going outside and looking in the sky, as well as how can technology support us. Great. Okay, so I think everyone could probably submit something for this. I think I'm going to go ahead and move on to the next slide since I think this has warmed up everyone's thinking. So as I mentioned, a lot of you were describing first-hand investigations, ways of engaging students in making their own observations, such as the sun's shadow and the moon's location in the sky. Obviously, I'm sure we're all aware that there are challenges to that. Any of us who live in locations which have more cloudy days than not. And of course, the moon is only visible to students for part of the month during the time that they're actually in school and in class. But these are ways that children can start engaging in carrying out investigations, constructing explanations from the evidence that they collect, as well as beginning to develop representations. So as I mentioned, these are challenges to do firsthand, so there's also ways we can engage students in secondhand investigations. So those that involve media such as simulations. So the ideas that I came up with that are based on the type of instruction that I've worked on with children and with teachers use simulated skies. So this could include a visit to the planetarium, as I've shown here, or it could include desktop planetarium programs such as the free program from stellarium.org. Some of you may be familiar with commercially available programs such as Starry Night, as well as some others. And this is a screenshot of what the stellarium sky looks like as the sun setting with a crescent moon in the sky. So these are ways that you can bring the sky into the classroom if you're not able to bring a portable planetarium to you or visit your nearest planetarium. This way, students can make observations that are not dependent on weather conditions, and you can also observe the stars and the moon in the simulated nighttime sky. So the ways that I've used these types of programs with children, so for example, the desktop planetarium program, you can actually have children collect observations. So many of you wrote about ideas of how you'd have the students record their observations. Well, they can actually record observations and get a practice of recording observations in astronomy using these simulated skies, recording what the phase of the moon looked like, and then you change to another day. What does the phase of the moon look like now? Or what direction is the sun rising in? What direction is the sun setting in? And another way that you can do this is, of course, the planetarium. Visit the planetarium. Make observations of how the sun, moon, and stars appear to move or change over the course of a day and night, or the course of a month or the year, whatever the phenomena is you're trying to focus on. But then it's also important that in any of these situations that either making observations outside, making observations on a computer screen in the classroom, or making observations in the planetarium, the children have additional opportunities to apply their observations. So one of the activities that I've done with first graders, and there's some pictures that I've put here of children doing this activity, is that after a visit to the planetarium where they observed, one of the things they observed was the apparent motion of the moon rising in the east and setting in the west. And during the planetarium, they actually used their physical motion to help them learn more about and to retain this memory of how things appear to move. They pointed to the moon and they physically traced with their arm the path of the moon across the sky. And they did that with the sun as well. And they could actually follow the sun and moon and see how they both appear to rise in the east and set in the west. And when they came back to their classroom, the children were each given, in small groups of 3, 2 or 3 children, a group of 6 images. And each image showed the moon, this is actually the full moon, at a different time throughout the night. So they had an image of the moon, for example, low in the east, and they had an image of the moon high in the south, and they had an image of the moon low in the west, as well as some intermediate images. And they had to use what they'd observed of the moon's apparent motion in the planetarium to order the moon in the proper sequence of rising and setting. And after that, you can see what the children are doing is they're creating their own representation of how the moon appears to move across the sky. And that's what these drawings are. These are first graders' drawings of the moon's apparent motion after learning through their own observations, and then this analysis, so that basically a data analysis lesson. And so, as I mentioned, these are spatially challenging ideas that we're focusing on in astronomy. So far, we've only looked at the sort of kindergarten through 2nd grade band of children making observations that can help them learn about the apparent patterns of motion of the sun, moon, and stars. And you could include starting to learn about how the phases of the moon change in this as well. But again, it's all based on their Earth-based perspective. But that's not to say that it's not spatially challenging. In elementary school, many of the third graders I've talked to, maybe they knew that the sun and moon appear to rise and set, but many didn't actually know that this motion is across the sky, that it moves from one side of the sky to the other. That's a spatially complex idea, this three-dimensional motion across the sky from east to west. Another of the challenges is the time scale. So in other concepts, areas that they might focus on in school, they're watching balls roll down ramps. They're doing observations of phase changes, from a liquid to a solid or a solid to a liquid. Here we're talking about time scales of motion that they can't actually see the sun, the moon, or the stars moving. They have to experience that in other ways. And the stars are especially difficult. The idea that they can see anywhere, depending on the location, dozens to thousands of stars in the sky. I've had children tell me that, well, they can't even, how could they possibly even figure out if the stars have moved? How could they tell one star from another? So until children start to understand and recognize constellations in the sky, it may be difficult for them to imagine that you could actually understand the stars as appearing to move across the sky as well. So one of the things that the NGSS recommends is that at these lower grade bands, that you only focus on the idea that the stars can be observed at night but are not visible during the daytime. And one of the ways that I found to be successful, both in my own work and looking at other people's work in engaging children in astronomy, especially at this age level and as we move up into the upper grade band, is to engage them physically in understanding these concepts. So as I mentioned, the idea of the sun rising and setting across the sky may seem very abstract. It's not something the children can touch physically, and yet if they're in an environment such as a planetarium or something where the teacher could actually trace out the path along the wall with a flashlight, the children could use their own arms to trace that path. And now that sensation, it's not just a visual observation, it's a sense they have from feeling it in their own bodies to recognize the change in location and the pattern of motion. Okay. So now, I focused so far on the Earth-based patterns of observation. And in the next section, I'm going to now move into the upper elementary levels and start to look at what's happening in space. So the idea of the Earth rotating, the moon orbiting, the distance of the stars, all of these things are where children need to start going, understanding that system that they can't actually see themselves, but how do those motions in space and our perspective on a moving Earth, how does that explain their observations of how the sun, moon, and stars appear to move, as well as other phenomena. So this complicated slide, I'm going to go through a few slides that look like this, shows on the right-hand side the phenomena that are described in the Next Generation Science Standards as essentially appropriate topics to engage students in at the grades 3 through 5. And this actually builds on what's being addressed at the kindergarten through second grade level. Apparent motion of sun, moon, and stars, daily changes in the length and direction of shadows. Those are actually kindergarten through second grade. But then we also have looking at the idea of the seasonal change in the sun's path, seasonal constellations. Moving up to grades 6 through 8, we start addressing more complicated ideas of tides, phases of the moon, eclipses, seasons, relative motion of the planets against the background of stars. And all of those phenomena that are observed from an Earth-based perspective can be explained by the motions and perspectives described on the left-hand side. And so to see the connections, I'll start by drawing in the connections between the Earth's rotation and these phenomena. Many of these phenomena depend on understanding how our perspective is changing because we're on a rotating Earth. Others rely on understanding that the the moon is orbiting the Earth on about a monthly cycle. However, some of these ideas require understanding multiple motions. So now we introduce the idea that the Earth is orbiting around the sun. Sometimes knowing where you are on the Earth affects your observations of what's happening out in space, as well as understanding the orbit of the planets. So the phenomena we're trying to explain are built on a model of motions in the solar system, but it's even more complicated than that because you have to understand why do these motions cause these phenomena we're trying to understand. And that's where it becomes extremely complicated and difficult spatially for students to learn. So in the next few slides, what I'm going to look at, let me go to the next slide, are some of the instructional examples. So one of the things that I found when looking at how instruction is designed, curriculum, assessments, etc., is that it often in astronomy focuses too much on what's happening in space, on learning that the Earth rotates, on learning that the moon orbits, which in my experience, those things are not actually very difficult for students to learn. I've had, many third graders after a very brief lesson agree, okay, sure, the moon orbits the Earth. But what is difficult is learning how to use those changes and those perspectives to explain our observations from the Earth-based perspective. So instruction, looking from the perspective of what is the next generation science standards trying to move us towards, is that instruction should help students learn about these observational patterns that we can see from the Earth and understand how to explain them using the scientific model of motions and perspectives in the solar system in ways that fuse the disciplinary core idea with the scientific practices. And this builds towards helping students understand that these celestial phenomena are not separate. We often teach them as now we're doing day and night, now we're doing phases of the moon, and now we're doing season. But what we're hoping to see is that students move towards a sophisticated understanding that all of these are just elements of an explanation that builds on a larger system. So I'm going to walk through two examples that take us through what I'm trying to explain here, this connection. The first example is from building on what we talked about at the kindergarten through second grade level of developing explanations for the apparent motion of the sun, moon, and stars. And that is from instruction that I worked with some third grade teachers. And then I'm going to go through an example at the middle school level looking at the seasons, which is an extremely complicated idea for students to understand. So this example, like I said, I'm trying to help students understand how the sun, moon, and stars appear to move from their perspective using this motion of the Earth as a rotating object in space and the moon's orbit and the distant stars. So in this example of instruction, students first needed to learn what are these patterns of motion from their perspective. And so they went to the planetarium and they spent about a 45-minute lesson making observations, engaging kinesthetically to follow the pattern of the sun, moon, and stars rising in the east and setting in the west. And they also learned about how the phases of the moon appear to change over the course of the month. And then they come back to their classroom. And so in the classroom lessons, they started by revisiting the path of the sun. And the teacher led the children in remembering that the sun appears to rise in the east and set in the west by using a flashlight to trace that path out across the wall. And then the students were led in not just being told that the Earth's rotation causes this motion, but they developed this understanding by actually physically rotating themselves. So the teacher introduced a model of the sun, so like a physical model, like either a yellow ball representing the sun or a light representing the sun, like a naked light bulb on a lamp. and had the children rotate to see how their perspective of where the sun was changes as they spin. And they also were given a small Earth globe to see how a given location on the Earth points in a different direction as it rotates, to see how the sun appears to move. And in the next lesson, they revisited the path of the moon. So now they add in, okay, the Earth rotates because, the sun appears to move because the Earth rotates. Now let's look at why the moon appears to rise in the east and set in the west. And so they add to their physical model in the classroom a physical representation of the moon, a ball, and so maybe one child holds the ball and another child pretends to be the Earth. And they see how their own physical rotation causes both the sun and moon to appear to rise and set over the course of a 24-hour cycle as the Earth spins. And then, on the next day, again, they're building on this scientific model. So this is really engaging them in using a scientific model and making predictions from that model, because now they can add stars to their physical model. They put little pictures of stars all around the classroom wall. And they then looked at how, as they rotate, do the stars appear to move? And from their perspective, the stars will appear to move. And they were able to then use that to compare that to the predictions that their model would make, that their rotating Earth predicts that the stars would appear to move. And they could compare that to what they actually observed in the planetarium. So this strategy of engaging children in this physical modeling activity that connects what's happening in space to what they can observe is an example of what can happen through a lot of phenomena. We do this often in teaching about the phases of the moon or other phenomena in astronomy. It's very complicated. The children that I've worked with, not all of them actually achieved the full scientific explanation, but there was significant improvement from where they started to where they ended, where initially most of them were not using the Earth's rotation to explain why the sun appears to move across the sky. And at the end, they were seeing how their motion on a rotating object allows them to perceive things appearing to move in the sky. That is an extremely complicated spatial idea, this idea of moving between an Earth-based perspective and their actual motion in space. So visualizing these motions can really help. The examples I gave were through going to a planetarium, using a simulation on a computer screen, or even just modeling that in the classroom where the teacher uses a flashlight to help them visualize what's happening. But they could also then visualize how things were actually moving in the solar system by using physical models. And the final complexity in this is this idea of timescale. So one thing I didn't mention was that once you introduce the orbit of the moon, things become a lot trickier. And children will often confuse the idea that the moon orbits the Earth with the idea that the moon appears to rise and set. And the moon does appear to rise and set once every 24 hours approximately, because the Earth is rotating. And it's not because of the Earth, because of the moon's orbit. The moon's orbit is much slower, takes about a month to move all the way around the Earth. But those time scales are very challenging for elementary students and certainly for even older students as well. All right, so in leading into now, that was the elementary example, which is, you can see, is quite spatially challenging and quite complicated for learners. Now we're moving into even a more difficult idea, and so this is at the middle school level in the NGSS, the reason for the season. So I'd like you now to think about your students, and if you don't have students for which seasons would be appropriate, perhaps just think your typical middle school student. Why do you think that middle school students, what do you think they would say is the reason why it's hotter in Philadelphia in June than in December? So we'll use the poll option for this.
And everyone, your poll button is now open and available, so you can find that right under your own name At the top of the participant window, we'll give everybody a few moments to read through the choices here and make your selection.
I do wish I had time to participate in all the interesting chatter going into the chat box. I will have to go back and read all of that after our session.
And it looks like most people have been able to put their response into the poll here. So thank you for that, everybody. And we'll keep this open for just another 5 seconds or so. If you haven't yet submitted your answer, you can go ahead and do that, and we'll get you in the total count here. Appreciate all of you who are interacting with us and giving us your feedback. This is really cool to see this coming in real time, and so that we can all kind of discuss and see what the group thinks. So we'll go ahead and lock that poll now, put up our graphs. I'll get it placed so we can all see and discuss. And Julia, I'll turn it back over to you to check out these results.
Great, thank you. Yeah, this is pretty much what I would expect too if I were to assess a group of middle school students, just general. They haven't had any significant extensive instruction on the seasons, is that they probably select something A, B, or C. There's a very common alternative explanation for the seasons that it's our distance that's changing enough that we have a different season depending on our distance from the sun. Whereas the scientific answer to this is answer D, which is actually focusing on the sun's altitude and how that affects how the rays are more concentrated on the ground in the summer compared to the winter. And so while some students may get that answer, most children and many adults as well find this explanation very challenging. One thing that you may notice is that we typically focus on using the Earth's tilt to explain why we have seasons. And so many students, if they're thinking just about tilt, may actually select answer A, thinking that we're literally tilting closer to the sun in June and tilting farther from the sun in December, which suggests that they don't understand the scale, another spatial concept. The size and scale is enormously important to understanding astronomy, especially as we start getting into concepts such as the seasons. So I'm going to walk through in this next slide how, both through my own experience in working with students and teachers in supporting learning of the seasons and how this is framed in the NGSS, what we need to think about in supporting students' understanding of this complicated idea. And I've broken it into basically 3 areas. We're not going directly from trying to answer why do we have different temperatures at different times of the year to the tilt. We have to go through an intermediate step. Now, obviously, caveat, the temperature patterns that we refer to as the seasons are not the same everywhere, and as we move closer to the equator, your students may have more difficulty understanding why we're trying to develop this explanation than students in more extreme latitudes that experience strong temperature shifts between summer and winter. But that's something else that we could discuss at another time or maybe in questions. But what I want to focus on is, to begin with, what I'm referring to as foundational patterns. So we're going to sort of assume that by the time we start to address the seasons, students are starting to think about a yearly change in the temperature patterns where they live. But what they may not be thinking about is how the length of day is also changing over the course of the year, and how the altitude of the sun is changing also over the course of the year. And the middle school students I've talked to are mostly unaware that the sun is higher in the sky in summer and lower in the sky in winter. And yet these are the areas that they need to understand to start developing that explanation. So at an intermediate level explanation of the seasons, it's still all grounded in understanding what we can observe from an Earth-based perspective, but starts to look globally, that we have a global pattern of temperature change, and that can actually be explained by the global pattern of differences in length of day over the course of the year, as well as that pattern of how the sun's altitude is changing over the course of the year. And that those two things, will change the length of day and the change in the sun's altitude, are actually changing the amount of energy that a given location is receiving. So that in the winter, if the sun is lower in the sky, the amount of incident energy is lower, as well as the idea that if the day is shorter, the sun is not up in the sky as long, there's less time for energy to be collected. So that results in a lower temperature. So like I said, all of that is just based on tracking observations of the sun. Those are things that are addressed in the elementary levels in the NGSS. Students need to start understanding that there's a pattern to how the sun's path appears to change over the course of the day, but then also over the course of the year. And I think there was earlier, somebody was asking about the relationship between the Earth's rotation and the seasons. And this is part of the reason why we need to understand the Earth's rotation, because now we're going to need to explain why does the length of day change and why does the altitude change. To understand that, you need to understand that the Earth, first of all, the Earth is rotating, causing the length of day, causing there to be a reason for a length of day and a path of the sun. So as we move into the final explanation, we're actually using the relative orientation of the Earth to the sun as the Earth is rotating on its tilted axis to explain the seasonal change in the sun's path that results in the change in length of day and change in altitude, and ultimately explain the seasonal temperature change. So this is not the kind of thing that you can really support students in understanding in a lesson or two. It requires a lot of time to build up an understanding of these patterns of observations and the correlations between changes in observations and changes in temperatures. But it does begin to allow us to engage students in integrating scientific practices in learning about astronomy. Obviously, if we're trying to help them understand temperature changes, patterns of length of day, patterns of the sun's altitude, we could communicate that directly and tell them that these are things that are happening. But if we really want them to understand and understand this deeply, they'll do so more, they'll learn this longer, they'll have a much deeper understanding if they're doing this through their own engagement in analyzing data, in developing representations as part of modeling and using models. And then finally, in the final explanation, they're going to need to have some form of model, either a physical representation of the Earth rotating on a tilted axis, or now we have computer simulations that also can engage them in this as well. And this is engaging them in the cross-cutting concepts that they need to understand across the domains: patterns, energy, size, and scale. All of this is important to helping them understand this phenomenon of explaining the seasons. And I think you can agree by looking at what I just walked through, this is incredibly challenging spatially. Understanding how to use data to create representations is an example of spatial thinking. Moving from that kind of representation, the idea that the length of day is changing in a cyclical pattern over the course of the year, and then relating that to how the Earth is actually rotating on a tilted axis as it orbits the sun, is another spatially challenging leap. So this is why we need to support them through either using physical models or computer simulations that help them visualize how these things are related. So with all of that, I think it's a good time to stop for questions.
Great, thanks, Julia. So we've been having some good discussions here, talking about some of the misconceptions and pieces. If folks have some questions specifically for Julia, they could put them up here. Julia, one of the things that we're sort of talking about in the chat area here, Julia, is the issue of scale, and students understanding of scale has an effect on how they think about some of these things. Would you like to comment on that at all?
Definitely. Size and scale is critical. At the elementary level, I was talking about the stars, and one of the things that I found that elementary students often believe, and a lot of this work has been with third graders, but I assume that it would continue up even middle high school if it's not addressed in instruction. The children actually believe that the stars are very small and located in our solar system. Many of them will say that they're located kind of around the moon. And so if we're trying to get them to use explanations about how the Earth's rotation affects observations, well, if you think that the stars are tiny and close to us, then sure, it makes sense for the stars to be actually moving out in space rather than being at great distances and their apparent motion being caused by the Earth's rotation. And we also, of course, see how important scale is in explaining the seasons. If you don't understand how tiny the Earth is compared to its distance from the sun, and then also how small the difference between how our distance from the sun in January to July, then it's easy to believe that a change in distance would actually cause the seasons. So instruction needs to carefully think about when do we introduce these ideas of size and scale, find out what the students' ideas are, and then challenge them by engaging them in really looking at the size and scale of objects in the solar system, and then also providing the scientific explanation to support them in moving to understanding how scientists explain the phenomenon.
Good. That's great. I think we're okay right now in terms of some questions, so why don't we move on?
Great. All right. In the interest of time, I think I'm just going to have everyone just think about this question for a second on their own rather than type it in for now. I think I have another interactive a little bit. What we're going to move into now is what should students learn about the planets and the solar system? So far we've been addressing phenomena that can be observed from the Earth, but we also maybe want them to know more than just explaining these kind of motions and patterns in the sky. So thinking about what you think might be important about learning about the planets and the solar system. And the way that this is framed in the NGSS is to think about how are we helping students develop increasingly sophisticated explanations for the Earth's place in the universe. So when asking what should students learn about the solar system, one of the ways to organize our thinking about instruction is to look at middle school as focusing on what we need to know about the solar system now, but then becomes evidence for something to be explained by the formation process of the solar system. So at the middle school level, we have ideas like generating explanations for the orbital motion and the dynamical nature of the solar system. The idea that the planets all orbit in the same direction on a plane is actually important evidence that is explained by how the solar system is formed. We can also look at, rather than focusing on what are all the distinct properties of the planets, like Jupiter has a big red spot, or Mars is red in color, or they're orange in color. Instead, we should look at how are we helping students understand the solar system in ways that we organize groups of objects according to their properties and locations, because those are things that are also explained by how the solar system is formed. That can then be addressed according to the Next Generation Science Standards, this is a topic for study at the high school level. So this is a stop and think. I'm not going to have you answer this in a poll, but it's something that I've been asking students across middle school, high school, and college in a research study that I'm doing that's really told us a lot about student thinking and how we design instruction. So the first question is, when asked why orbiting planets do not escape from the sun, what might students say? And when asked why orbiting planets do not crash into the sun, what might students say? So in the interviews that I've been doing and my colleagues have been doing with, like I said, middle school, high school, and college students, we often find that the first question, though many students aren't quite sure why planets stay in orbit and don't escape the solar system, others will say, oh, gravity. Gravity, something, maybe they're not quite sure what gravity does. They may not know if it's either a push or a pull, but gravity has something to do with keeping planets from escaping the sun. But now, if you turn your question to, well, okay, gravity's keeping the planets from escaping. So there's a pull, maybe there's a pull between the planets and the sun. So then why don't the planets crash into the sun? And at that point, this often is one where students can't explain. They may think that there's some sort of, well, some balance. They're far enough out that the pull isn't enough to pull them into the sun. Or maybe there's some barrier that prevents them from crashing into the sun. That's actually something we hear a lot when asking them why the moon doesn't crash into the earth, that there's a barrier that keeps it from doing that. So these are the kind of ideas that we need to start trying to address in instruction. And so in the next slide, I want us to think about the way that Newton kind of proposed thinking about this. And this is Newton's canon. And so if you want to use the poll button on this one, the question is, a large cannon is firing shots tangentially to the Earth's surface. Cannonball A hits the Earth while Cannonball C begins orbiting the Earth. What might explain the difference in these paths, the trajectories of Cannonball A and C?
And we'll give everybody a few moments to check out the options for responses there. Appreciate your quick response on this one as we head into our final section here. It looks like most people have been able to submit their answer, so just another 5 seconds, and then we will lock the poll so we can take a look at what everybody thinks on this question. Great. Thanks, everybody, for jumping on that poll question. We'll go ahead and put up our graph.
Great. So looks like most people here are thinking about the scientific explanation of that the cannonballs had different initial velocities. What we found with talking to students is that when asked why planets orbit the sun, very few are actually talking about velocity or inertia. They talk about gravitational interaction, but have difficulty communicating and understanding of how velocity is actually part of the explanation. And we've also found that instruction often underplays that or ignores the role of an object's inertia in understanding orbital motion. And even when we start to support students in learning about this, they confuse inertia with a force, that there's a force of gravity keeping a planet like a moon pulled towards the Earth, but that inertia is a force in the other direction. So this is an area we found that students need a lot of support in understanding how velocity is part of the explanation of orbits. And one of the ways that I've seen this started to been done successfully in instruction is through a simulation from SET. Some of you may be familiar with set.colorado.edu. These are simulations that allow students to engage in scientific phenomena. In this case, students are actually able to do an investigation where they can modify the initial velocity of the planet and its distance from the sun and use this as evidence for claims about how objects form stable orbits. So what you see in this example, here's a teacher guiding her students in a conversation where they develop a scientific explanation based on what they've observed in their own investigation. So rather than just teaching this as a direct instruction, students can engage in the practices of science through this simulation. Other ways that we can engage students around the solar system in the practices of science include understanding why we think the solar system is flat. Because I've also talked to a lot of high school students who are not actually aware that the planets orbit all along the plane, that they can understand orbits without actually understanding that the solar system is flat. And so in this example, the teacher had students use the computer program Starry Night, like Stellarium that I was telling you about earlier, to make observations of the planets and asteroids and their location above or below the ecliptic. The ecliptic is the path that the sun appears to take through the background of constellations. And that forms our plane, the Earth's orbit around the sun. And so the teacher guided the students in understanding how their observational evidence from an Earth-based perspective is evidence that the solar system is flat. And she then used that evidence as to have a conversation where the students critiqued a physical model of the solar system that did not display the planets clearly on a plane orbiting in the way that they learned based on their evidence. And another example, often, like I mentioned, we teach planets by looking at individual properties of planets. Here's an example where a teacher, with her students, generated a large table on the whiteboards across her classroom. And along the top are written all of the planets. And along the left-hand side is a column of data such as the distance, the mass, the density, the temperature, the number of moons, rings, etc. So that the students were then asked to use that data to form their own groupings of objects in the solar system, so that the physical properties and locations were used to form categories of objects, but it wasn't beginning by telling them this is the way scientists do it. The students could actually argue based on the evidence the way that they think makes sense to group planets. And all of these experiences then become evidence for how the solar system formed. And once they understand things like the planets orbit in the same direction on a plane, that the inner planets are rocky while the outer planets are gaseous, or that the planets and moons show evidence of heavy bombardments, lots of craters from an earlier period where lots of things were still moving in the solar system, all of those can be explained by how the solar system formed from a cloud of gas that collapsed to form the sun and the planets. And so if you want to see a nice, succinct, about a 3 to 4 minute video, I've included a link here that you can go watch and understand how the solar system formed and think how that links back to what we know about the way the solar system is now. And so in my final slide, I just wanted to show an example of some students now discussing, engaging as a class, how the model of the solar system explained all of these other properties of the solar system that they've been learning about. And so as a final slide, this is just another one of the performance expectations that addresses all of those ideas of the connections between what we can observe in the solar system now to how the solar system was formed. And I'll conclude by just pointing out this idea that the way that the NGSS moves us through the solar system, through astronomy, is to think about how this is going from direct observations of phenomena towards using data sets collected on or around the Earth, including data gathered by satellites in Earth orbit and beyond, towards using scientific models to explain these observations and integrating key scientific practices. So I will stop there and turn it over to Ted.
Great. Thank you very much, Julia. And just a few points here to touch base on. You can find the standards at nextgenscience.org, or you can also find them on the NSTA website at nsta.org/NGSS. Also at NSTA, you can find discussions in the Learning Center, or we also have a member-only listserv, including one specifically about NGSS. We'll have 2 more Earth and Space Science web seminars this year, 2 weeks from today, November 19th on Earth Systems, and then Earth Activity. And after the first of the year, we'll be doing some on life science and engineering design. Also, you can find archives on the practices, cross-cutting concepts, and the earlier ones we've done, Disciplinary Core Ideas, at the NSTA website, as well as a number of journal articles about NGSS in our various journals. Upcoming in December, a great online short course with Emily Morgan, author of Picture Perfect Science. And you can see more information about that at the link below. If you're interested in the framework or the standards, you can get them in the NSTA bookstore, as well as a reader's guide to the framework and a reader's guide to the standards. And we also just recently released Translating NGSS for Classroom Instruction by Roger Bybee. Roger was one of the authors of the standards and tries to go through and talk about how you can take the standards and move into planning your classroom. If you don't have it yet, I highly suggest grabbing the NGSS app, it exists for Windows, for Android, and for Apple, and you can use it for the phone or a tablet. Always good to have. I am literally heading out the door tomorrow morning to Charlotte, North Carolina for our conference. I hope to see some of you there. And later in December, we'll have one in Denver. And I hope all of you are going to be heading out to Boston in April for our conference. A lot of activities being planned around NGSS for your benefit. And with that, I'll hand things over to Bryn, but just really thank Julia for really shedding some light on Earth and Space Science here tonight.
Well, thanks a bunch, Ted, and I agree with you. Wonderful job by Julia for today's focus on Earth, Space, and the Universe. Fantastic information, and thanks for the interactions as well. This was wonderful, and thanks to you, too, as well, Ted, for facilitating our Q&A. We do want to thank the Carnegie Corporation of New York for sponsoring the web seminar. I also want to thank the administration of NSTA for their support for web seminars. And just wanted to remind everyone about the NSTA, the web seminar collection in the NSTA Learning Center. The collection is a great place to find not only the presentation slides and the archive, but also related journal articles, lesson plans, and those science objects and side packs that have information and simulations multimedia related to the content today. So check that out. I also wanted to remind everyone to check out our upcoming web seminar calendar. You can register for these programs and more by going to learningcenter.nsta.org/webseminars. Thank you, everyone, for participating with us today, and we look forward to seeing you again soon on another